right, good morning, everyone. Hope you're all well. Who's ready to continue with our GIS exercise from last Thursday? Good to go? All right, so right now I'm gonna give it one more minute for other people to join, but in the meantime, open up your GIS file from last Thursday and we will continue on.
Scott, when will this assignment be due?
End of the, I technically put it down as end of class today, but I'm gonna make it end of the day today in case anybody needs to work on it after class.
Okay. Yeah, because I'm having trouble with my GIS and I contacted geez, I forgot her name, the Ramtech
Oh,
lady.
Diane.
Yeah, and she still hasn't got back to me.
Yeah, she's crazy busy this semester, and yeah, even with me, like when I email her, she takes like 4 or 5 days to get back to me.
Okay, yeah, same. I emailed her from the last class and she still hasn't got back to me. So
Yeah, as a workaround, you can use the computers at NESB or a bunch of the computers at Morgan Library have ArcGIS Pro. Or the other option is to use the virtual desktop infrastructure and log in remotely. And the instructions for that are on Canvas. In modules under computing resources, there's instructions for how to log in remotely.
Okay, yeah, I feel like that's probably what I'm gonna have to end up doing.
Yeah, it's unfortunately it's just been like kind of they for some reason Esri just makes the licensing a little more complicated than it needs to be.
Yeah.
It used to be the kind of thing where I just provided everyone with a serial number and they installed it and you're good to go. But now that they have this kind of login system, it's just complicated things.
Yeah.
So, yeah, those are your options. So,
Okay.
all right, let me share my screen.
Josias, is the problem that you can't log into it? I had the same problem, but I was just using the wrong username. I didn't have CSU Rams at the back of it. I don't know if that's your problem too, but
no, yeah, because like the username is like usually like for mine obviously it would be like Chavez 77 or whatever, and then I added that like underscore CSU Rams, and it still was not working.
huh? Okay.
So I don't know what it is. I don't know if it's issue with licensing. Yeah, I can't figure it out.
So I took what is it again? GIS 319 last semester, and I still can access to the GIS. So I don't know if you guys still can do that, but yeah, I still have access for that. So I'm still using the same the same account that I used as a GIS 319 last semester.
I'll try that. I'll see if I can log into my old account or something.
All right, so yeah, I'd say Josiah's just just kind of I guess follow along with what we're doing so that it's more familiar when you do it later when you get access to software.
Yeah, that works.
All right, so we were talking last week about our little friend here, N. quadrivitatus, and the habitat available to it in City Park. And so some of the questions down here as a chipmunk researcher that we had already answered were minimum and maximum patch sizes of the ideal habitat, the mean patch size of ideal habitat, how many patches of ideal habitat meet or exceed the minimum viable patch size. We answered that one. The percentage of the landscape that's ideal. And I think we're up to number 5, which is what percentage of the landscape is effective habitat for N. quadrivitatus. And so in order to do this one, we need to think about what we mean by effective habitat. So if we look at the text and the diagram that I've provided up here, basically the chipmunks are, they prefer to be under tree cover, but they're willing to be exposed for a maximum of 20 feet. So basically what that means is that if there's more than a 20-foot distance between patches, they will not run from patch to patch. They'll stay in the patch that they're in. Or they'll temporarily kind of run, let's say, a little distance out from the patch they're in. If they can't find anything, they'll come back in. So what this means is that in order to find the effective habitat, we're going to want to take the existing patches and look beyond their borders. And there's a tool in GIS. So let's go back into the software here. We have our patch areas here, and we want to figure out the area for the extended distance for the effective habitat, right? And so there's a tool in here. If we go to analysis, the analysis tab up here at the top, there's a tool called Buffer. And you can also find it if you just click on the tools button, which opens up, I'm going to move the zoom menu out of the way, which opens up your geoprocessing menu on the right side. And in here, you can either choose Buffer, which is usually listed in the top section here, or you can just type in Buffer and it'll bring up that tool. So Buffer basically just takes the outline of all of the polygons on a given feature class layer and offsets them. So similar to the offset tool in AutoCAD. And so by using this, we can kind of figure out what the effective habitat area is. So I'm going to go into Buffer, and it's asking for the input feature. So our input feature is going to be this ideal habitat layer. So I'm just going to grab that layer. Whoops. I'm going to grab that layer from the contents pane and just drag it and drop it into my input features over here. We'll give that a second to get added. And then it's asking what should the name of the output feature class be. And instead of ideal habitat, I'm going to call this one, it wants to call it ideal habitat buffer. I'm just going to call it effective habitat. And again, you can't have a space in there because you can't have spaces in the name of a feature class. The distance that we're measuring is linear units, and underneath linear unit, we can choose what the unit is. So in this case, what kind of units do we want to use?
Feet.
Feet, correct. So we'll choose feet. What distance do we want to use for the offset value?
20.
20 is a good guess, but it's incorrect. Can anyone tell me why? What's that?
Well, I was thinking 10 feet, because if you have 10 feet on each side, then it would make 20 total. Is that?
That is correct. Yeah. So the chipmunk's only willing to be exposed for 20 feet. So if we did 20-foot offsets, then we would find matches where the chipmunk was actually exposed for 40 feet because they're running 20 foot out from one patch, 20 foot into the next patch. So we actually want to do an offset of only 10 feet. So I'm going to set 10 as the distance. We'll leave the rest of this the same. And then the last important thing here is what's known as a dissolve. So first, we're going to run this without the dissolve, just so I can show you what the result is and why it's not desirable. And then we'll rerun it again so that you have better understanding of what dissolve means and how that's going to be helpful in this process. So first, I'll run it with the no dissolve set as the dissolve type. Before I run it, let's go into environments here. I'm going to set my output coordinate system. If I drop this down, I'll just set it to the current map, and that'll give me the Colorado Central state plane system so that, again, when we do computations and measurements, they'll be as accurate as possible. Once I have all that set, I can click run. And this will not take too long. It's creating the layer now. All right, so it created the layer. So what we're going to do now is I'm going to zoom in on this. And So what you can see here that we've created is that in dark green, we have the original ideal habitat. And then in this bluish color that's outlining it, we have the effective habitat. So without the dissolve, one of the problems that we run into is that each individual patch gets its own offset, right? So we have places here where we have offsets that are bordering on the offsets of other patches, and each one of those is going to be measured separately. That's not what we want to do. We actually want to measure the total effective habitat. So we want to be able to measure this as if it's all one area, wherever those offsets are intersecting each other. That's a place where a chipmunk can run from one patch to another because they're at or less than 20 feet of distance apart. So that's why we need to use the dissolve. What the dissolve does is it finds all the places where these individual offsets intersect, and it basically merges them together as if they're one big shape. So we are going to delete this effective habitat layer. So I'll just right click on it and choose remove. And likewise, I'm going to go into my catalog here. I'll go into my databases, my Chipmunk City Park, effective habitat. I need to make sure I delete it from there as well. So I'll just right click on that and I will choose delete. All right, so now we can rerun that process, but this time with the dissolve option turned on. So again, I'll go to my analysis tab. I'll click on the buffer tool here. That'll open up my buffer geoprocessing tool, grab ideal habitat and drag that in as the input feature. Change the output feature name to effective habitat. Again, no space. Linear units, set our units to feet, set the distance to 10 feet. And then this time under no dissolve, we're going to drop that down and we are going to choose dissolve all output features into a single feature. Is that what we want? No, actually, I think it's the second one. Dissolve all features. Yeah. Actually, we want the second one, sorry. Because if we choose the first one, dissolve all output features into a single feature, it'll choose everything, whether they're connected or not, and make them into one giant feature. We don't want that. The second one is dissolve features using fields unique values. And then we're going to use the dissolve, we're going to leave dissolve fields as blank. And what that'll do is it'll just merge together all of the areas that are just based on geometry that are overlapping each other. If we wanted, we could merge things together based on other criteria, but we're going to leave that blank. And again, I'll go to environments. We'll set output coordinate system to the current map. And once that's all set, we'll click run, and now we'll see the difference in the output. And this is taking a little bit longer because the dissolve process is being added in now. All right, so now if we look at the areas where it created the offset, notice what it did, right? Where it created the offset, but it merged them together as one big shape wherever the patches are within 20 feet of each other. And that's exactly what we wanted. So if I turn off my ideal habitat layer, now I'm just looking at my effective habitat layer. And we have obviously a lot more area of effective habitat because now we're basically merging together patches that are within 20 feet of each other, right? And if I click on one of these, that's not what I wanted. I'm gonna have to redo this again. So this actually did what I didn't want, which is that it merged them all together into one giant shape. And in fact, if I go to the attribute table, yeah, there's just one object in there. Okay, I chose the wrong option. Sorry about that. So we're going to do this one more time. So third time's a charm. Let's remove effective habitat. Let's go over to here. I'm going to delete it from my geodatabase. And we're going to run that tool one more time. This is something that happens a lot in GIS. You choose some wrong options. It doesn't create the output that you want. You just have to redo it with different options. Not a big deal. All right, buffer. Let's bring ideal habitat in as our input feature. We'll change the output feature class to effective.
So is it the first dissolve type, the dissolve all into single?
It should be, and that should give us what we want. And if that doesn't work, then there's another option we can do, but I'm pretty sure they changed these dissolve options. There used to be a third option that was just dissolve everything based on geometry. They took it away for some reason. And I think they combined it with one of the other ones. So I think the second one should work. So we'll.
I just did the dissolve all into a single feature and it did the same thing.
That's annoying. Okay, in that case, then we are going, there's a separate dissolve geoprocessing tool that we can use to get what we want. So I'll just run this again, effective habitat, feet, 10 feet. Yeah, I don't know why they changed it. Like that third option was a really useful one. They decided to get rid of it for some reason in the latest update. So we'll just leave this on no dissolve and we'll run this once again. And we'll get overlapping buffer areas, but then we can join those together using a separate tool that's called dissolve. So you can see all of our overlapping areas here. And if I click on one of these features, it's only selecting the one feature and not the whole thing with all of the overlap. So we're going to fix that by doing another geoprocessing. So I'll click in tools. And this time I want to look for the one that's called dissolve. And here we go. Here's dissolve. And now our input feature class is going to be effective habitat. And so we will drag that in. Actually, before we do that, because this is turning out to be an intermediary step, I'm going to go back into the catalog here. I'm going to change the name of effective habitat. I'll call it effective habitat. Here, let's call it effective habitat temp. And I'll do the same thing here. I'll change the name to effective habitat temp. There we go. So we'll go into our geoprocessing and I'll drag effective habitat temp into the input features. Output feature class will just be called effective habitat. Dissolve field, we're going to leave that one blank because we want it to be done based on geometry. Do we want to create multi-part features? The answer is no. So we're going to uncheck. What a multi-part feature is basically where you have separate objects that are not touching each other that are still joined together as if they're one object based on some commonality, usually from the attribute table. We're going to turn that off because we only want objects touching each other to be joined together. We'll go into environments and we'll change this into current map again. So we have the state plane coordinate system. This should give us what we want. Hopefully, let's click run and we'll let this dissolve.
Yeah, it worked for me.
Awesome. All right, so now I'm going to uncheck my effective habitat temp, and then effective habitat. If I click on a shape here, yes, it's only selecting the shape I wanted. Questions?
Can you go back to the parameters? Can I see the?
Oh, sure. So here we go. Yep. So you want to use your effective habitat temp as the input feature. The output feature class is just effective habitat. Everything else you leave blank, and make sure, this is important, make sure you uncheck create multi-part features.
Yeah, thank you.
You're welcome. All righty, so I'm going to close this attribute table down here. So now what we have is the offset. If I turn my ideal habitat back on, we can see that we have a 10-foot offset of all of the patches. And wherever they overlap, they merge together to create these sort of much larger patches, right? So what used to be these lots of individual isolated patches here are now effectively joined together as one larger effective habitat patch. And that's exactly what we wanted. So now let's open the attribute table for effective habitat. So I'll open attribute table. All right, and so now let's go back to the question we're trying to answer. So what percentage of landscape is effective habitat for N. quadrivitatus? So the effective habitat is obviously going to be a larger percentage, right? And in this case, we just want the grand total area of all of the effective habitat, right? Whether or not it meets or exceeds the minimum patch size requirements. So again, we have a shape area list here. This is probably the correct shape, the correct area for each one of these patches in square feet. But just to be sure, I always like to recalculate it. So again, we'll go through that process of adding a new field. And we'll make the name of this new field is going to be effective habitat patch area. The data type will make it a double because that gives us the greatest accuracy. Then we'll go into numeric here, change the category to numeric. I don't need a decimal places because the nearest square foot is close enough. We'll show the 1,000 separator. And again, for the suffix, I'll put a space and then SF for square feet. So we're going to get the total square footage calculated for each one of these now effective habitat patches. So I'll click OK. Once that's all done, we can close that. It'll ask if we want to save the changes. I'll say yes. And now we have this new. Yep, go ahead.
Sorry, it was kind of fast.
Oh, sorry.
I can keep up with that.
Yep. So again, you click on Add Field. And I set the field name to effective habitat patch area. And then I set the data type to double. And then under the numeric format here, or the number format, I changed it to numeric, 0 decimal places, check the box for 1,000 separators, and then change the suffix to SF for square feet. Are we good?
Yes, thank you.
Great. All right, I didn't make any more changes. All right, so effective habitat patch area, now we need to calculate that. So I'm going to right click on effective habitat patch area. I'll choose calculate geometry. And down here, the property that we're going to calculate is the area. And then it wants to know the area unit. I'm going to choose square feet United States. And then the coordinate system is going to be the current map, which is the state plane coordinate system. Once I have all of that good to go, I'm going to click on OK, and this is going to go through and calculate. They should match shape area, but it's always a good idea to check just to be safe. And indeed they do. So these are just rounded to the nearest foot. So 7590, 7590, they do match. But again, makes me feel better to know that I calculated and I'm definitely using the correct numbers. All right. So what do I want to do next now to find the total area of all of the effective habitat?
Scott, sorry, after making that field,
Yeah.
do I need to click anything to see that in the attribute table? Because it's I just
It
don't
didn't show up.
Yeah.
So if you close there's the tab open that says fields, and you need to either hit the save button at the top when you're in that fields window, or just close it and say yes to save changes. If you just click on the tab to go back to your attribute table, it won't show up yet until you.
Oh, gotcha. Okay.
Any other questions?
Sorry, and then how did you calculate all the area in there?
Yep, so you right click on that field on effective habitat patch area, click on calculate geometry. And then you just want to, next to the name of the field there, you just drop down property and choose area. And then it asks what area, what's the unit you want to calculate it in. We'll drop that down and we will choose square feet. And then you want to make sure the coordinate system is set to current map. So that's using the state plane coordinate system. And it should change it to NAD 1983, 2011 State Plane, Colorado Central.
Gotcha. Thank you.
Yep. And then we have our calculations for the square footage of effective habitat patch area. All right. So what is the next step to find the total effective patch area now that we have all those calculated?
Right click and go to statistics.
Correct. So I'll right click on that. I will go to statistics. Right, and here it's showing us all of our statistics in the panel on the right side. It also shows us a graph of the information down here at the bottom. So if we come over here, the sum is what we want, right? So this is 7,369,780, if we round up, 785 square feet of effective habitat. And let me get my notes from last class over here. When we measured the total park area at 16,574,925 feet. Again, your numbers might be slightly different, but shouldn't be dramatically different unless you chose to include the golf course to the north of the park. And by the way, if you did choose to include the trees in the golf course, make sure that when you're measuring your park area that you draw a rectangle that goes all the way up and includes that golf course as well. For me, I'm just doing the city park area. So we're going to divide this by the total park area to get the percentage that is the percentage of the park that is effective habitat. So I've opened my calculator. Let's bring this onto the correct screen. So in this case, we have 7,369,785 divided by 16,574,925, and we get about 44.5% of the park that has effective habitat. So you guys should have gotten something very similar to that. So that answers, let's go to our assignment sheet here. There we go. So that answers the question, what percentage of the landscape is effective habitat for N. quadrivittatus? And finally, we have one last question, number 6. What percentage of the landscape is effective habitat that meets or exceeds the minimum viable patch size for N. quadrivittatus? Right? So now we need to go back and see what was the minimum, the minimum viable patch size for a self-sufficient population. And up here, we said that it was 1.25 acres of contiguous habitat, right? So in this case, we're doing 1.25 acres of contiguous effective habitat. So now what we want to do is go back to GIS, if I can find it. Here we go, go to our effective habitat. And what we're going to do is we're going to sort the effective habitat patch area by area in descending so that we get the largest ones at the top. So I'll right click on that and I'll choose sort descending. And so now they're sorted with the largest patches at the top and the smaller patches down towards the bottom. So now we need to, I forgot what the number was for 1.25 acres in square feet. So I will just open up Google and I will ask it 1.25 acres in SF. And it will tell me it's 54,450, right? Remember we did this last time? So now we want to find all the patches that have at least 54,450 as their square footage. So we can close that. And what I'm going to do is I'm just going to use these boxes on the left here. And if I hold shift, I'll go down to the first one that's under 54,450, which is this patch right here. I'll go to the one just above it. I'll hold shift and click, and that'll select all of the patches that meet or exceed the minimum viable patch area. So now we're at 10 patches. I seem to remember that when we did this the first time with just the ideal habitat, we were at 3 patches, or maybe only 2
It was
patches.
4.
4, okay. So we've more than doubled the number of patches, right, that meet or exceed. So let's go back to what that question was. So what percentage of landscape is effective habitat that meets or exceeds a minimum viable patch size for N. quadrivitatus? So that means we want to add up, we want to get the sum for all of these selected ones, right? And the way we can do that is down here at the bottom, we have 2 options. There's a button that shows all records, meaning it's showing all the patches regardless of what's selected. The one next to it only shows the selected records. We want to click on that. And you'll notice that now the list is only showing all the patches that we selected that meet or exceed that minimum patch size that we need of 1¼ acres. Everyone with me so far? So we're on the button showing only the selected records. And now what we're going to do is right click on effective habitat patch area again. We'll do statistics once again. And this time it's only going to show the statistics for the selected patches, right? So in this case, our sum is where it should, or is it still showing the grand total of all of them? 7 million. Did anyone write down what the number was last time?
That looks like the same number as before.
I think it's the same
Scott,
number.
you have data set and then you have selection next to it. So data set is everything, and then right next to that would be your selection row.
Thank you very much. Thank you. So again, that's another thing they changed. They used to do it where when you went into just the selected records, it only showed you the selection. Thank you for pointing that out. So yes, so here for sum, here's the total data set sum. Here is what we have selected. So it's the 4,139,383. So now in order to calculate the new percentage of landscape area that is meeting or exceeding the needs for a self-sufficient population of N. quadrivitatus, we'll divide that by the total park area. So I will go back to my calculator, and we'll go to 4,139,383 and divide that by the total park area of 16,574,925. And here we have about 25% of the park. Or 24.9, yeah, it's going to be exactly 25% here. So what was the answer last time when we did the other option, just the ideal habitat?
2.8, I think.
For percentage, what was it? Say that again.
Mine was 2.8, but I was zoomed out a little bit farther, so that doesn't.
2.8%.
I had 24.
Yeah, I think 24 is about right.
Yeah, I think I remember 24.
Yeah, so so now our new percentage is at 25. So we've gained 1% of landscape by considering the total effective area, right? And so that answers our 6th and final question on this sheet. So what I would like you guys to do, again, post your answers to all of these questions that you got for your specific data set in terms of what you selected as your tree canopy area and what you selected as your overall park area, and post those along with a map that shows both the ideal and the effective habitats for N. quadrivitatus. So if I go back to ArcGIS for the map, all you're going to do is zoom out.
So one map each, or
No, I would do them in
one map each, or one?
I would just make it one map total. So if let's go back to map and I'll deselect, clear my selection. If I turn on ideal habitat and just move that to the top because it's smaller. So now all in one map, I can see the park area, I can see the ideal habitat, and I can see the effective habitat all in one map. So I would recommend just showing it this way as one map, and you can just do a screen capture of that, attach it to your PDF, and then that's your submission. Any other?
Do a layout with a scale bar and a north arrow?
Nah, don't even worry about all that.
It was a joke.
Okay, good. So, yep, just a screen capture of this and you guys are good to go. Any other questions about what you guys are submitting for this?
So is this just due by the end of today or whatever?
Yeah, by the end of the day. It says on Canvas, it says end of class, but as long as you get in by like, midnight tonight, then you'll be fine.
Cool.
So we're just turning in the map. We don't
No,
have to
you're
like
turning in the
export
map.
features to different.
You're turning in the map plus the answers that you got to the 6 questions.
Yeah, okay.
List, which are probably slightly different than what I came up with, but should be pretty close.
Okay, great. Thank you.
Yep. Anyone else?
Recording, right?
Sorry, say that again. Something about the recording. So, well, I don't know who said that, but anyway, yes, this is all being recorded. This will be posted on Canvas under modules, just like the other recording. So the recording from last Wednesday is already up there, or last Thursday is already up there. And today's will be up there within a few hours once YouTube and Zoom are done processing the video file. Are we good? All right. So with that, I'm going to close ArcGIS. I will save my Chipmunk City Park project. And we are going to move on to the new material. Let's close this. Go to PowerPoint. And open this up. So let's take a little poll here. I'm going to stop sharing for a second so I can get a feel. So how many of you would like you shouldn't need much time because we basically worked on it in class, but how many of you would like to have like a little 10 minutes now to just get that done and submitted right now versus moving on to the new material? So raise your hand if you would like to just have like, we'll just say 10 minutes now to get that all done and submitted. 1, 2, 3, 4, 5, 6, 7, 8. Wait, let's see. I see. Wait, 1, 2, 3, 4, 5, 6, 7. Okay.
It's gonna really matter for me, Scott.
It doesn't matter for you, but all right, we'll take 10 minutes. So it's 10:10 right now. We'll take a little break until 10:20, and then we will start our next presentation, our next lecture. So you have 10 minutes to get that wrapped up for the activity and get it submitted to Canvas. So I'm going to mute everything here for 10 minutes. I'll see you guys at 10:20. All right, we are back. And hopefully that was enough time for you guys to get that work submitted. If not, like I said, you have until the end of the day today to get that submitted. So don't worry if you need to submit after class today. All right, so next we're going to move on to some new material here. So let me once again share my screen. All right, so since we've been talking a lot about patches and specifically habitat patches, with that last exercise that we did looking at the N. quadrivitatus habitat in City Park, it's time for us to kind of do a deeper dive into patches and get a better understanding of how patches operate, what their characteristics are, and how they impact the overall mosaic of the landscape. So first, go back to an overview of patches. So as you recall, the definition of a patch in landscape ecology is an area of habitat differing from its surroundings in appearance and/or composition, often the smallest ecologically distinct landscape feature in a landscape mapping and classification system, right? So in the photo shown below, those forested areas in the middle of all those agricultural fields are the patches. Right, and here's another diagram showing again that the three big components, right? So you have the matrix, which is the most predominant landscape type. In this case, it's suburban development. You have the patch, which is a large contiguous area of the landscape type that you're interested in studying. In this case, it's the forested areas. And then the corridors, which are the smaller, they're basically be thought of as small linear patches that connect together larger patches. Right, so within this, the forested areas are the patches, similar to when we're looking at the tree canopy in the City Park example. And as a reminder, patches can and do operate at different scales. So for example, the scale of a patch for a black bear is not going to be the same as the scale of a patch for a sage grouse. And you need to study the landscape structure at the scale of the organism that you're concerned about, right? So an organism that has a range in terms of the area that it uses to go through its life cycle, if it has a range of 500 acres, you're going to be looking at patches at a different scale than an organism that has a range of only 1 acre. So you need to keep that scale in mind and make sure that the patches that you're focusing on are appropriate to the organism that you're studying. Right, and it's also important to note that the paradigm of patches, corridors, and matrix isn't the only way of understanding heterogeneous landscapes. There's also a competing concept that's called the gradient model, which we haven't really talked about yet. We've been talking up until now as if patches and corridors and matrix are all very separate, distinct types of things, but they're not always seen that way. So in this example, we see an aerial orthophoto of a landscape area on the left. The representation in the center is the patch corridor matrix model, also known as the PCM model. And this is the one that we've been familiar with so far, where we have more or less clearly defined patches and corridors that are within a distinct matrix. And then on the right side, we have the gradient model. And the gradient model argues that there are no clear-cut edges and that all changes across landscapes occur incrementally across gradients. So in this case, the amount of forest is measured on a pixel by pixel basis from the low amount of tree cover to a high amount of tree cover, right? So if we're looking at this diagram, it's basically showing the same things as we see in the orthophoto and the PCM model, but it's showing it as percentage of forest or percentage of tree cover, where the darker green areas have a higher percentage and the more tan areas have a lower percentage, right? So this is arguing that there aren't really these hard boundaries. Like you can't define where the forest stops and the matrix begins. You're actually, it occurs across a gradient. And so what we realistically find is that there isn't really any one right answer, and that both models have their advantages and disadvantages in terms of measuring how landscapes function. In general, though, the patch matrix or patch corridor matrix model tends to be more appropriate for human modified landscapes, whereas the gradient model is a better representation in more sort of quote unquote natural environments. And since we're looking at landscape ecology from the viewpoint of landscape design and land planning, we're primarily going to be looking at it from the patch corridor matrix model viewpoint. We will, however, look at the gradient model a bit more when we get into looking at spatial landscape metrics towards the end of the semester. Right, so here the patch corridor matrix model, more appropriate for human modified landscapes, and then gradient more appropriate for quote unquote natural, where you tend to have more of a gradient from one landscape type to another. The reason that PCM model is more appropriate for human modified landscapes is that humans, you know, we tend to have a very profound impact on the landscape, and there tends to be a very hard boundary between where the forest stops and the agricultural field begins. You don't find that nearly as much in more naturalized landscapes. So next we'll look at patch origins. So thinking about where do patches come from and how are they created in the first place? So these are broken up into several different types of patch origins. The first one is known as an environmental variability patch. And environmental variation patches are basically patches that occur naturally in the landscape as a result of differences in the physical geography of a place. So things like slope, temperature, microclimate, soil moisture, elevation, and other factors. And various types of ecosystems are going to be adapted to particular environmental conditions and therefore are limited by these geophysical factors, right? So if you have a certain type of tree that likes high soil moisture and grows better at lower elevations, then the patch size that particular tree will cover is going to be limited by topography and soil moisture. This is an example here in some upper elevations where the coniferous stands of forest prefer the drier land on the slopes of the hillsides and naturally form patches where the right conditions exist in that landscape, right? So this is, again, we're seeing these patches of conifers and they're not being contained by any human modifications to the landscape. It's just based on where the correct growing conditions for that species exist in the landscape. The next patch type is known as a disturbance patch. And these are patches that are created by, as the name suggests, by disturbances. So things like mudslides, avalanches, windstorms, ice storms, herbivore outbreaks, mammal trampling, and other natural changes, which can give rise to disturbance patches. Right? And so in this case, we see an example from fire where there used to be a much larger area. Part of the landscape has burned, leaving behind a disturbance patch. Right? Or you can consider the burned area itself as a disturbance patch, right? Because that fire created new conditions in terms of soil moisture and nutrient content and tree cover and things like that. They're going to favor different species than the ones that are established in the forested areas on the west side of this roadway down the valley down here. Then there are also introduced patches, and this is the first type of patch that comes about due to human modification. So when humans introduce organisms to an area, an introduced patch is the result. And it resembles a disturbance patch in the sense that disturbance of a small area initiates the patch. And in all cases, the introduced species, whether they're plants, animals, or people, exert a dominating and continuing effect on the patch. So there could be planted patches, for examples, or homes or habitations that create an area around them that becomes a new patch. In this case, the introduced patch is an area of agriculture next to this little building here. And this is an introduced patch in the matrix of forest that existed there previously. And then our final type of patch, and really the type that's most common and the one that we'll be dealing with most often in landscape ecology from the point of view of how it, the implications it has for landscape architecture, are what is known as remnant patches. And remnant patches are typically caused by widespread human intervention in a landscape, where that human intervention leaves behind these smaller patches of previously existing landscape types. So this example that we're seeing in this photo is where previously forested landscape has become dominated by agriculture with small patches of the original forest area remaining. Remnant patches generally are the result of habitat fragmentation. So habitat fragmentation is kind of the big impact that we have when we have this type of these remnant patches showing up in a landscape. And that brings us to the definition of fragmentation. So fragmentation is defined generally as the process or state of being broken into small or separate parts. Or from a landscape ecology point of view, the breaking up of habitat or vegetation type into smaller, disconnected sections, generally as a consequence of human land use patterns. So again, here we have an example of an area that was previously, all forested, that's now being gradually taken over by agricultural uses and leaving behind these remnant patches, resulting in habitat fragmentation. Right, so this is an example of what it can look like when you have forest or habitat fragmentation. So this is an example of an area that has a contiguous forest cover. And, you know, maybe it starts out with like some small places individually, but as development expands in the area, you get more and more fragmentation of that landscape, right? So it might start out initially with 1 or 2 homes or a small farm, but inevitably those settlements tend to grow in size. You get more farms added to the area, and you get larger and larger habitat fragmentation.
Scott?
Yes.
Can you just do that graphic again?
Sure. Go back and I'll hit this, and it just kind of gradually fades in little pieces here. Right. And we'll see, actually in a couple of slides, I have a website where you guys can go and look any place on the earth and see habitat fragmentation in action. So this is just a diagram that shows habitat fragmentation and forest fragmentation worldwide. Forest fragmentation is a huge problem around the world, as demonstrated in this diagram. So areas in brown in the diagram are forest areas are heavily fragmented by human activities and uses. And perhaps even more important than the absolute area of forest being lost each year is the pattern in which it's being removed. And we'll see some examples of that a little bit later in this lecture. So, but as opposed to leaving remnant forest areas in one large patch, forest fragmentation is thought to dramatically increase the risk of local and even global extinction of species that can't adapt to the fragmented habitat, right? So in green, we have unfragmented. In brown, we have highly fragmented, and then in tan are areas that haven't really been assessed yet. But you can see in the areas that have been assessed, there are huge areas that have been heavily fragmented due to human activities. And there is a website that was put together by Carnegie Mellon Institute that looks at, or Carnegie Mellon University, that basically has pulled together 30 years of time-lapse aerial photography for the entire Earth. This is the website down here. is https://world.time.com/timelapse. And in fact, I have, I'll click on that. I have that page open. Let's bring this over here so you guys can see it. Can you see that website? So this is the time-lapse website, and I have an area selected here. So this is the time-lapse website. Let's see if I can make this larger. I can't, but this is an area. So it goes from 1984 up to 2018. And what it shows is it's basically just aerial photos from every year in between. And this is pretty frightening because this was what the Amazon, an area of Amazon rainforest looked like back in 1984. If I hit play, it'll just kind of time lapse through each year up to current day. So if we hit play, you can see the level of development that happens here. And you can see that fragmentation getting worse and worse. So that's 2018, right? It's just kind of crazy to think about how much fragmentation, how much Amazon rainforest has been lost due to farming and burning practices. So if we go to 1984, that's what it was originally: unbroken, completely contiguous forest cover. And then by 2018, it looks like this. And you can go just about anywhere in the Amazon rainforest, and this is what it looks like today, as opposed to what we think of as this like continuous area of tropical rainforest. So this is having a tremendous and devastating impact on all kinds of wildlife species that rely on contiguous areas of rainforest in order to survive. Let's close that. All right, so the other thing I'd like to show you is, actually this should not be called fragmentation time-lapse, but this is a short video that talks about some of the other ways in which fragmentation is having a huge impact on our environment and even on human health, because it doesn't just impact the species that directly rely on it, but also has a knockoff impact on human health. So this is actually, what time is it right now? 10:40. I'm going to save this. This video is a little bit too long. So what we'll do is we will start off at that point in the presentation when I see you guys on Thursday. So that is it for today. Any questions about anything we covered or what you're turning in for the in-class assignment that we worked on? All right, that's it then. I will see you guys on Thursday.
Scott,
Have a good one.
Thank you.
Scott, I have a quick question for you.
Sure.
I've been trying to log into the remote learning, and it's not allowing me to do that either.
When you say remote learning,
I mean, sorry, the remote desktop.
oh, okay. You followed the instructions and like set up the Pulse Secure.
Yeah, I set up Pulse Secure, and then I set up the Microsoft Remote Desktop connection. And then I was able to create like the workspace.
Mm-hmm.
And I kind of connected to it, and it like brings up the HLA, and then it says like 2020, 2021 year. And then when I click on that, it asks me to connect again. And that's when it's not allowing me to connect.
Huh. Honestly, I don't know all the ins and outs of the VDI system. The ones that you'll want to contact if you're having trouble with it would be the Ag Help Desk.
Okay.
So you can shoot them an email and let them know. Probably the fastest and easiest way to get on the software is just going to be to go into one of the computer labs.
Okay. Yeah, it's because the issue is that I'm down in Denver. I'm not in Fort Collins right now.
I see. Okay. Yeah, then definitely contact Ag Help Desk and let them know you're having trouble with it. If you need a little bit of extra time to get that activity turned in, then that's fine.
Okay. Yeah, I'll let you know as soon as I hear back from the Ag Help. Okay. Thank you so much, Scott.
Yep. Good luck.
Yep. Bye.
Bye.